Hello, so let us solve the problem now. In this problem, I'm supposed to calculate a double integral and the domain is defined in that way with two inequalities. Okay. First thing, you see that the integrand here in this integral is extremely simple. But first of all, I want you to understand that this is still a function of R2 to R, because whenever you are dealing with a double integral, it means that your integrand should be interpreted as a function that takes an ordered pair and gives you one single real number back. So what I'm trying to say is that don't say that this function that you see is f of x equals to x. Yes? No, this is a wrong way of interpreting that, because if you write it in that way, it means that you are having function f, which is a function of one single variable, but we are working in two dimensions because I'm solving a double integral. So even if the output does not depend on any y, but still your interpretation should be that you have a function f of x and y is equal to x. What does it mean? It means that every point that you give to this function gives the first component back, okay? But you are giving still an ordered pair to your function and giving you one single number back, yes? Okay, so that is one. The second point is that I want to sketch the domain of this that you see on the board with hand, because I want you to understand this is possible. But then I want to put everything in GeoGebra because I want you to see a very good picture about the continuation of the problem, because I want to solve this problem in two different ways. First, I want to use the symmetry arguments, which is a little bit delicate, especially if you don't understand what are the underlying rules for symmetry arguments when it comes to computation of integrals, double integrals, triple integrals. And then I will also solve this problem using the usual way of solving a double integral. Yes, and then you will see that how life-saving is the symmetry arguments if you really know how to argue for them. Okay, so if I want to understand my region, I have to consider two inequalities. Y is greater than or equal to this. If you have watched the previous videos, you know that whenever you want to do that, first you need to concentrate on equalities. Okay, for example, if I want to understand that, I will actually say that y equals to 2x squared minus x. Okay, so because I will clean these messy pictures, so I'm not worried about that if they are a little bit messy. So that is my x and y coordinate. And this is a very standard parabola, yes? So for drawing a parabola, so you need to know where the minimum point or maximum point is, roughly speaking. So the derivative of this function is 4x minus 1. And if I equate it to 0, so you get x equals to 1 over 4. So it means that, by the way, and then this is positive, so I have a parabola with a minimum point. It occurs at 1 over 4, but what is the minimum itself? I have to put it back here, so y becomes 2. 1 over 4 to power 2, it's 1 over 16, and then I have minus 1 over 4. So it is 1 over 8 minus 1 over 4, which is minus 1 over 8. Okay, so let me exaggerate a little bit the scales here because I have to deal with fractional numbers. If I take this one to be, so 1, 2, 3, and 4. Okay, so this is, assume that this is 1, and this is a quarter, and then half of it should be minus 1 over 8, so half of it. So something like this. Here is my minimum point. Yes? So I don't want to write the numbers on top, so this is a quarter, and this is minus 1 over 8, and that's the minimum of that one. On the other hand, I know that when I put x equals to 0, y also becomes 0, so this means my parabola passes through the origin as well. Okay, and then if I put, by the way, if I put y equals to 0, that is better. If I put the y equals to 0 and factor x out, it becomes 2x minus 1 equals to 0, so either this one is 0 or that one is 0. X is 0 is here, and this one is 0 means x is 1/2. So x is 1/2 is here. So anyway, hopefully you agree with me, this is a rough sketch of my parabola. Yeah, it's hard to draw them in a good way. I will switch to GeoGebra soon. Okay, so that's my parable. But on the other hand, I want you to know the inequality. So if you remember, I told you in the previous videos that if you want to know which region is acceptable or which region is represented by this inequality, you need to pick a test point. A test point is a point that you know its location perfectly well. For example, here in this case, it doesn't hurt if I take that one. So the x-coordinate is 1 over 4, yes? And then the y coordinate is 0. So if I put that in this number, what do I get? Instead of y, I put 0, and instead of x, I put 1/4. So if I do that, you will see that this inequality holds. This is a simple calculation I want to do with yourself. So instead of y, you just put 0, and instead of x, you put, I already did that, by the way, I got -1 over 8, and 0 greater than or equal to -8 is right. So it means that if I ask you which region is represented by this inequality, you will tell me this side of this parabola which contains my test point. So as far as this inequality is concerned, I am within this parabola. Okay? Now, I want to draw that one. Of course, you know that x equals to that one is no longer a function. It's again a parabola. But you see immediately the role of x and y are being interchanged here. So either I have to redraw the parabola, or I can interchange the role of x and y. So this means that I will have this scenario. I don't know if I can draw it. So this means that I will have this one switched here, and this one in the middle, and then I will have -1 over 8 here, and then I will draw another parabola here, which passes through the origin as well, and it goes like that, and then I will go here. Something like this. Okay? So this is the parabola. I want you to remember the numbers, yes? So here it is 1/4, here it's also 1/4, this is -1 over 8, this is also -1 over 8, yes? And then I want to skip this part, but again, you need to know where this inequality is referring to. If you pick this test point, you will see it is referring inside this parabola. So on the one hand, I have to be inside that parabola because of this inequality. On the other hand, I have to be inside this parabola because of that inequality. So finally, this is the domain. This is the domain D that I want to work with. Okay, so I hope that it is important for me to know the extreme points. Perfectly fine. It seems to be 1, but in principle I have to calculate it. So let me calculate this intersection point. So I have to solve a system of equations. The system of equations consisting of y is equal to 2x squared minus x, and x equals to 2y squared minus y. I have to solve this system and see how many solutions are there. Based on our picture, if I have done something, if I have done it good, then it means that you expect 2 points of intersection. One is, of course, the origin, and it is easy to guess. x0, y0 satisfies simultaneously both equations. And there seems to be there is another one, which is 1. But in principle, you have to confirm that that is true. So let me solve that system of equations. For example, I write y is equal to, wherever I see x, I replace it with this one, substitution method, yes? So this becomes 2, and then I have 2y squared minus y, and then to the power of 2 minus 2y squared minus y. And let me simplify that and solve that equation. It seems hard, but I don't think it is hard because I see I can 1 y's cancel. So let me just write that. I raise it to power 2 and multiply it by 2, so 4y to the 4th and multiply it by 2. 2 times the first one times the second one, and then multiply it by 2. And then the second one is squared multiplied by 2. And then I have minus 2y squared plus y. So what happens? This 2y squared and that 2y squared are gone. This y and that y are gone if I move them. And these two terms are left for me. So this means that 0 is equal to 8y to the 4th minus 8y to the 3rd. I factor 8y to the power of 3 out, so this is y minus 1, and then this means that y is either 0 or y is equal to 1. So that our guess was correct. So my picture is not that bad, by the way. Okay, so if x is equal to 0, I put it here, y becomes 0. If y is equal to 1, I put it here, x becomes 1. So this point is actually the point 1 and 1, and this point is 0 and 0. Another thing that, of course, if you don't have a graphical tool in hand, you need to be careful, because usually parabolas can also be like this, you know. Okay? I cannot draw, but what you understand what I mean. Do we have a sharp point here, or they are really passing through? Definitely you understand that they are passing through. There is no sharp point here, because if that's the case, I will have another intersection which is also here. Yes, so this is not happening. So it's a really smooth curve, like an almond or something. So you can just rely on it. Okay. So what I do, I pause recording. I will clean this. We don't need them, and I will try to do it on GeoGebra for a better picture. Okay. Okay. So I want now to put everything in GeoGebra. Okay. So let me also give you access to GeoGebra. Okay. So what I do. Okay, so before going to GeoGebra, you know that, according to the calculation that I made for you, you know that I am only interested between 0 and 1. As far as this parabola is concerned, this region doesn't have anything to do with this branch of my parabola. So I go from 0 and to 1. So instead of drawing the whole parabola to confuse myself, I give instruction to GeoGebra to draw only this part. And I don't need the other part. So let me keep the picture clean. Okay? So the way that you can do it in GeoGebra, so you can write function. Okay, and then you choose that function. Function start value and end value. So you choose that one. So the function is what? 2x squared minus x. So that, 2x squared minus x, that is my function. My starting value, we decide to make it 0, and the final value, we decide to make it 1. Okay, but this is so small, so if you don't mind, let me just increase the size a little bit. So first of all, let me just move it here, and now zoom in to make it bigger. Okay, so that's good. Yes, I'm getting some numbers here. So that is just that part of my parabola that I need. Okay, so if I want to do the same thing with GeoGebra, but I want to use a trick, because I remember that. By the way, you know that if x and y are interchanged and one equation is transformed to the other equation, it means that they are symmetric with respect to the line y equals to x. Okay, so I want to use this trick. So what I will do, I go back to GeoGebra here, and then I will actually draw a line. This line that I am drawing is actually, so let me just do this line, yes. This is the line y equals to x. And I ask GeoGebra to reflect this red parabola with respect to this line. Definitely it becomes the other parabola, yes. And how we can do that? So I can go here to this instruction. I use reflect about line, and then I click on my parabola and that one. Okay, so it will give me the other parabola. But the point is that I want to differentiate between these two curves. So I would recommend you do this by going to setting and change the color. Yes, so I will change the color to something that I can see good. So let me make it, for example, green. Okay. Okay, so this is the region between this green parabola and the red parabola, excluding this black line, is the region of integration. And it's exactly according to what we more or less predicted there. And this point of intersection, as you see, has coordinates 1 and 1. Okay, so I also want to define points for technical reasons in GeoGebra. I want to make it available for me. Yes, this point is 1 and 1. And then I don't need this, by the way, for the time being. I don't need this line, so let me hide it. Don't show me the object. Don't show me the object. Okay, so that is my domain. Whatever you see inside is your domain. But the point is that, you remember, you're supposed to integrate over this function. How can I visualize this? Okay, so first of all, let me go back to GeoGebra. I want you to understand that is not a correct argument. Yes, I just connect these 2 points. Everything is totally symmetric. So, but if you think you can calculate your integral on one of these subregions and then multiply it by 2, because the region is symmetric, that is not correct. So the goal of this exercise, the goal of this problem, I want to use, so you see, I chose this problem because the integrand is so simple and the domain is completely symmetric according what you see. But still, if you have this feeling, I have this experience that some students have this feeling that as far as the domain is symmetric, you can calculate the double integral on one part of the domain and then multiply it by 2 to find the whole integral. Okay, but you have to be careful. Not only the domain should be symmetric, but also the function should be symmetric, how it treats on those regions. What do I mean by that? Hopefully I can show it to you. So for doing that, I need to go to one dimension more, because when you're dealing with integrals, and double integrals, the geometrical interpretation of a double integral is a volume. Volume of the object, which is confined with this domain on the xy plane, and the surface represented by the graph of the function from above. So this is the volume of that object. Of course, if it is lying above the xy plane, and if it is below the xy plane, it is exactly the same volume with a negative sign. Okay? So this is the geometric interpretation of the double integral, and it's very good to know. Okay, so let us go back here to GeoGebra. So I drew this one. This is completely symmetric, no magic. But still, if you have the feeling that, okay, I can calculate my integral on this part and multiply it by 2 to find the whole answer, this is wrong. To understand that, I go to one dimension more, so I change my view to 3 dimensions. The good point about GeoGebra is that still you see that one, so let me make everything right. So let me move this a little bit here so that you can see that. And we also go change that one. So let me here, okay, I choose that one. And then let me make it a little bit more beautiful so that you can see. That is exactly the same picture on 3 dimensions from this picture. And this is so small, so if you don't mind, let me also zoom in a little bit, because I want you to see what is happening, okay? And I don't want to distract you with a lot of numbers there, but that's the same shape from that one. Now I asked GeoGebra to draw the graph of my function, but my function is extremely simple. The function is f of x and y equals to x. But you know that if you want to draw the graph, this should be interpreted as z. And you already know that z equals to x is not complicated at all. It's a plane. Yes, plane containing the y-axis and bisecting the angle between 2 coordinate planes. So let us go back and confirm that, okay? So I go here, click here, so to activate the 3D view, and then I ask GeoGebra z equals to x. And that is your graph. So let me make the 3D graph a little bit more visible, and I hope that you understand what is going on now. So you see, you lose the notion of symmetry if you go to 3 dimensions. You see, I hope that you agree with me that if I calculate the integral on this part, what I am calculating? I am calculating the volume restricted with this domain from below and restricted by this plane, oblique plane from above. And it is not equal to the volume of the other part. Yes, because the other part has this region Okay, and one part of the region, the function goes below the x-axis, you see, so below the xy plane. So one part of it is negative. Yes, if you calculate this integral on this part only, you will get a negative value. Yes, I hope that you understand that the symmetry argument does not work. It is very clear on this picture. Yes, so if you integrate on this region, you get the volume on top of this region restricted with this plane. But if you calculate the integral on the other one, this part is positive, this volume, and the other one becomes negative. So I hope that you understand that your expectation is not that correct if you just calculate 1 and multiply by 2. But still, I found a way that you can still use symmetry arguments to solve that problem in a little bit strange way. So how? This is the point. So let me try to explain this on the board now. Okay, so what I want to do, how can I use the symmetry argument? Okay, so you have some, I can also show, I can keep the picture for you here so that you can also have access to it somehow. Okay, so what I want to do here, I drew this line, if you remember in GeoGebra, you can see this still on the display. And then what I want to show, this is the whole thing is my D, but I want to write here D1. This region, I call it D1. And this region, I call it D2. So what is happening? D is the whole region. So if I ask you what is the relation between the region D and these two subregions, you would tell me that if you union these two regions as sets, I will get the region D. Moreover, there is no overlap between these regions, yes? Except, of course, that line. So this means that my question mark is equal to the double integral on the region D of this function dA. But because D is the union of these two subregions and the subregions have nothing in common, I can decompose my integral on, instead of D, I can do it once on D1 and then plus double integral of x dA on D2. This is very clear. This is a very standard theorem. Okay, but the interesting point comes here. I will write it down and then try to motivate you why this is true. So I will copy and paste the first part without any changes. Okay? But I do some changes in the second part. So this I just copied and pasted here. But here what I do, I change D2 to D1 again. This is a crucial argument. But I will change x to y, dA. So my claim, I want to, because this is just a copy and paste of this part. I want to convince you, based on symmetry arguments, in a little bit convoluted way, that these two expressions, these two integrals have the same value. That is important. Because if you just understand that, then the calculation becomes straightforward. Okay, but why these two values are the same? Okay, so in order to convince you that these are the same, so I would do this. I will define two functions. So f of x and y equals to x, and g of x and y equals to y. So f gives me the first component, g gives me the second component. If I ask you what is this one, this integral is actually defined using the Riemann sum, yes? Sorry, this is x. So if I ask you how should I calculate this, what you do, first of all, let me replace x with the function name. Okay, but I want you to understand that, okay? So what we do for calculating this, I need to write a Riemann sum. But what is the meaning of the Riemann sum? So it means that you start partitioning your region D2 to, for example, let me clean this a little bit. So you start sweeping the points. What do I mean? You pick a point. So first you need to partition your domain. And each domain, you need to, for example, let us have this rectangle here, and then very small rectangle around that. And what you do, you will pick a point there, and then the coordinates of this point, say, is x and y. Okay? And then you take f of x and y and multiply it by the area here, which I call it delta A. And this is one of the terms in the Riemann sum defining this integral. So you get a contribution coming from this point, and then you change to the next point. You get another contribution because x and y are changed, and f of x and y is changed. You get different contributions coming from different points, and then you add them up and calculate the limit when this delta is extremely small. So something like this, yes? So, but focus on one typical point of my region with coordinates x and y. So I start actually considering the contributions coming from every point, but suddenly at some point I reach to this point, and this is my contribution. Okay? If I ask you what is the value, you will tell me that f of x and y, according to the definition, gives the x coordinate, which is a number, and then I'll multiply it by delta A. This is the amount of the contribution coming from this point on this region for the function f. My claim is that if you do the same thing for region D1 with function g instead, at some point you get exactly one number like this. And I want to continue this argument point by point. How? For the second integral, so integral of y dA over d1, you can imagine this is g of x and y dA over d1, yes? So what we do now, we go here, again, I will start picking a point, any points, and then I calculate g of x and y of that point and multiply it by d of a. Okay, but when I want to do this, I have to consider all the points, one by one. At some point, I reach to very particular point. Which point? The mirror image of that point with respect to this line. Okay, so I am doing the same thing. I am taking points on this region and calculating g at the coordinates of that point, multiplying it by delta A. This is the contribution coming from that particular point. And if I continue this process, for every point that you see here, finally at some point I have to touch this point. But if I ask you what are the coordinates of that point, you will tell me the coordinates of that point is the mirror image of that one with respect to y equals to x. It is yx, y and x. So when I am just trying to find all contributions, when I reach to this point, then I have to put the coordinates of this point to my function g. But g function gives you the second coordinate. So it will give you the second coordinate, which is x again, and then times delta A. So if I ask you what is this, you will tell me this is the contribution of the function f on region D2 at this point. If I ask you what is this one, you see that is exactly the same number, but that is the contribution of g function in the region D1 when I reach to this point. So I hope that will convince you that for every point that you choose in domain D2 and gives you a contribution for the double integral over that region, you have exactly one point from the other region which gives you the same contribution if you choose g of y and x to be y. So if you choose this function. Okay? So I hope that I could convince you that actually these two integrals are the same. And if you believe now that they are the same, the continuation is more or less simple. Because now again, I can combine them back. You see, d was decomposed to two integrals with d1 and d2. Then I replace this one with d2 and write it d1. And then now I have two double integrals on the same domain, so I can collect them back. Yes, so I can write integral, double integral of x plus y dA on domain only d1. Yes, so that is domain d1. So this means that I have to calculate my integral only on domain d1, but not of the simple function x, a little bit more complicated function x plus y. So that's the idea. That is the symmetry argument behind that. So the price that I paid in this symmetry argument is that, of course, my integrand is a little bit more complicated. Instead of x, I have x plus y. But then what I have to do, I have to so to calculate this double integral only on this domain here. So let me have this in my hand. I want to calculate, I only consider this a small domain here. But then it is easy, because you know that the highest, I want to give the role of free variable to x. The lowest value of x is 0. The highest value of x is 1. So if I just do that, so I want to write integral, and I want to give the role of free variable to x. You see that x goes from 0 up to 1. Yes? And then I have another integral. The integrand is x plus y. And then I have dy. But where y is going from to where? So you need to understand that one as well. So you see, you choose any point here, any point for your x coordinate. For example, let me just take this one. And then if I go vertically up, you see that one side of that red line is on this curve, which I know its equation. It's y is equal to 2x squared minus x. On the other hand, this is the equation y equals to x. And this will not change during this interval. Yes, even if I go here, choose x to be here, then still, of course, this length is changing, but the lower part is still on the same curve, and the higher point is still on the same line. And even if I continue going here, you see that then I have this point and that point on the same parabola, on the same line. Even if I go further, the same parabola, the same line. So this means that for every choice of my free variable x between 0 and 1, y goes from the equation of this parabola, which is 2x squared minus x, up to equation of this angle bisector y equals to x. Okay, so finally, I hope that you are convinced now that I can write 2x squared minus x, and the upper limit is x. And then I have to calculate this. Okay, so let us just do this quickly. This is not hard. It's just normal calculation. So if you don't mind, let me call it I of x, because this is an integral. I call it I, but if I integrate over y, x variable is left, so I call it ix. So if I ask you what is ix, the integral of this one is very simple. I am integrating this function with respect to y, so the integrand x, the derivative becomes xy. And the second one is 1/2 y squared. And it goes from this curve and x. Okay? So what I have to do, I have to replace y with x. So this becomes x squared plus 1 over 2x squared. I replace every y with x minus. And then I replace every y with 2x squared minus x. So this becomes x, 2x squared minus x. And then plus 1 over 2, 2x squared minus x to the power of 2. So, okay, now we continue this. So this becomes 3 over 2, x squared, then minus. So I multiply this in. What happens? It becomes 2 x cubed plus x squared. Yes? But then this is the first one squared. 2 times the first one times the second one, and plus the second one squared. And I have a minus 1/2 that I multiplied there. So it becomes minus 2x to the 4 plus 2x cubed minus 1/2 x squared. Yes? So I double check that, so everything is right. I multiply that in, so this is correct. Okay, then what happens? This one and that one gives me x squared. There is also another x squared here, so it gives me 2x squared. So I consider these things, not to mix things up, so let me take them away. And then fortunately this one and that one are totally gone, and I am left with this one. Yes? So this is my Ix. But then I put it here, it becomes integral from 0 to 1, and then I have 2x squared minus 2x to the 4th dx. Okay? So I can factor a 2 out, and then the integral of that one is x to the power of 3 divided by 3, minus integral of that one is x to the power of 5 divided by 5. And then it goes from 0 to 1. And then what happens? This is 2. I put 1 here, it's 1 over 3 minus 1 over 5. But when I put 0, it is 0. And then I solve that. So the answer becomes 2 minus 3, 2, yes. So it is 4 over 50. Okay? So that is the solution to this problem. Okay? Okay, now let me solve the problem without using the symmetry argument, and you see that the problem becomes lengthier than the previous case, and then you will appreciate the symmetry arguments even more. Okay, the first thing that I want to tell you is that I want to motivate you that you have to break your domain into two parts here. So this is your whole domain, which is between the green and the red curve, this almond shape, and I want to integrate my function here. So my integral is the double integral over this region D, which is the almond shape, and the function is simply x and then dA. Okay, so you know that if you want to calculate this integral directly, first you have to decide about which variable, x or y, you want to consider as your free variable. Then you will see that it is inevitable. You have to break down the domain D into two domains and then calculate the integral on each domain separately. One of them will be this. I will argue shortly why this is the case, and the other one can be taken this big one in total. So I want to argue for this that you have to calculate this integral once on this small domain that you see here, and then on another time on this bigger domain, then add them up. Because first of all, the union of these two domains makes the whole domain, and there is no overlap between these two domains. Okay, let us assume that we want to give the role of my free variable to x. What does it mean? If you consider the whole domain, the lowest possible value for x is here, which is minus 1 over 8 according to the previous calculations. And the highest value of x is here from 1. So it is completely clear that the lowest value minus x is somewhere between minus 1 over 8 and 1. Okay? Then let us see what happens for the y value, for the y coordinates for my domain. Okay, let me choose a point for x in this interval. Let us just choose this one. And for this point that I have chosen for x, I want to know what is the lowest y value and what is the highest y value. What I am supposed to do, I have to draw a vertical line that passes through my domain. Okay? And then you see that after that, this line is going outside my domain. Before that, the line is also going outside from my domain. So my line in my domain is limited between these 2 points that I'm highlighting now. And this point is the lowest y value for that particular x, and this is the highest value for that particular x. And you see that the lowest value lies on the red curve and the highest value lies on the green curve. Okay, so remember that for this particular choice, The lowest one lies on the red curve and the highest one lies on the green curve. Okay? What happens if I go, for example, choose a little bit higher value for x? So let us choose somewhere between 0.6 and 0.7. What happens? I want to still, for this particular value of x, I want to know the limits for my y. What I do, again, I draw a vertical line so that it cuts my domain and goes out of it. So you see that this line enters the domain here and goes out from my domain at this point. So the lowest value of y is this much. From here to here is the lowest value, and from here to here is the highest value. But still, even though these lowest values and highest values are different from the lowest and highest values in the previous case, but still the point is that the lowest value lies still on the red curve and the highest value still lies on the green curve. And I hope that you understand that this situation does not happen. It does not change if I start from here and up to here. Whatever x I choose from 0 up to 1, the lowest y value lies on the red curve and the highest y value lies on the green curve. But the situation is not the case if I choose x somewhere between -1/8 and 0, which is also acceptable. What happens in that case? Say, for example, I choose this particular value for x. I do the same thing. I draw a vertical line to cut my domain, so I have to go upward, and then you see that I have two cuts. This is the lowest y value for this particular x, and this is the highest y value for that particular x. But this time, both the lowest and the highest are lying on the green curve. So this needs consideration. So you cannot start varying x from -1/8 and have a specific lowest value for y and the specific highest value for y for all choices of x in this interval. It is inevitable. You have to break it down the way that you consider x. For x's from -1/8 up to 0, your choices are on these branches of the green curve, and between 0 and 1, the choices of y are between the red curve and this branch of the green curve. I hope that you agree with me. If I still want to give the role of the free variable to y, sometimes giving the role of free variable to y makes the problem easier. Instead of you might be able still to solve the problem with one integration rather than breaking the domain into two distinct parts. But hopefully you agree with me, this is not the case here. If I want to give the role of my free variable to y, then it means that the lowest y value is here, which is again -1/8, and the highest y value here, but the same argument goes on even in that direction. I recommend you to think about this problem again yourself, to actually train your brain about how to think about the domains. So it seems that it doesn't matter if I want to look at the problem vertically by choosing x as my free variable, or if I change my point of view and look at the problem horizontally by choosing the y-coordinate to be the free variable. Nothing changes. I still have to calculate two integrals on two different domains. Okay. Another thing that I want you to know about, so now you understand there is no difference, so if you don't mind, let me give the role of my free variable to x. Okay, so now what I will do, I will consider this one domain 1, and I will consider the bigger one domain 2. So then I will break my integral to two integrals, yes? One integral of the same integrand x dA on domain d1, which is the green part, plus the double integral of the same function on the other domain d2. Okay.
I think in this case would be easier if I start with calculating the integral on the second domain. There are some delicate points about the first one, which I discuss about that later. But now look, if you restrict yourself to this domain D2, okay, then the least value for x is 0, the highest value for x is 1. Okay, so let me call this one I2, integral 2, so let me start calculating integral number 2. So I want to give the role of free variable to x, so it means that I have to consider this integral with that one. Of course, in this domain, x goes from 0 to 1. I have another integral left. My integrand is x. Now integration over y should be done. But what is the appropriate limit for the y variable if x is somewhere between 0 and 1? It is easy, so I convince you that it doesn't matter if you choose x here, doesn't matter if you choose x here, anywhere between 0 and 1, whenever you choose x and then do the vertical line, the lowest y value is on the red curve, and the y value for the red curve is exactly in front of your eyes, 2x squared minus x. But the highest value that you see is on this green curve. That's good, but it means I need the y value. But unfortunately, the equation given for this curve expresses x in terms of y. What I need to express y in terms of x. So it's easy. I solve a quadratic equation. So let me just solve it here. So I will actually write 2y squared minus y, and I move this x to the other side, so it becomes minus x equals to 0. And then I will say that y is equal, I use ABC formula, 1 plus or minus square root of b squared, which is 1 minus 4 times a times c, which becomes positive 8x, and then divided by 2a, which is 4. And let me, by the way, write it in this form. I can write it as 1 over 4 plus or minus 1 over 4 square root of 1 plus 8x. As you expected, I get two answers. But this is important. You see, this is always non-negative, and this is 1/4. So one branch is 1 over 4 plus a non-negative number, which is greater than or equal to 1 over 4. The other branch corresponds to 1 over 4 minus a positive number, which is less than or equal to 1 over 4. On the other hand, this line is exactly y equals to 1 over 4. So this means that the branch whose values of y are greater than 1 over 4, which is this branch, is represented with this equation with positive sign, and the other branch is represented by the same equation with negative sign. So that is crucial. So this means that which one of these y's I should choose, you see, when you choose your x somewhere, for example, between 0 and 1, for example, this point, and when I go upward, I will never hit the green curve below 1 over 4. I always hit the green curve which is above 1 over 4. So definitely the y value is the positive one. That is crucial. So what I have to do now, the lowest value for x, so for y variable, in terms of the given x is equal to 2x squared minus x, 2x squared minus x, and the highest value is this one with positive sign. So this becomes 1 over 4 plus 1 over 4 square root of 1 plus 8x. So you already see some indications about calculational computation if I do not want to use symmetry arguments. But I find it myself fun to solve the same problem from different perspectives. By the way, it will teach you a lot of math if you are stubborn and don't give up easily. You will understand the concepts much deeper and more reliable if you try to do this. This is a good habit, I would say, if you develop in yourself. Okay. Now what I do, I will come back here and calculate this integral. The integrand is actually extremely simple, and by the way, x is also considered to be a constant because integration variable here is y. So what I do, I will write it as equal. I have an integral from 0 to 1. I have a big pair of brackets here, and then I have a dx at the end. But now I concentrate on calculating this integral. But that's also simple because this is just x. The integral of dy is simply y. So this becomes xy. And I have to run it from 2x squared minus x up to 1 over 4 plus 1 over 4 square root of 1 plus 8x. Okay, so what can I do now? Instead of y, I plug this in, and instead of y, I plug this in, and then I subtract. Okay, so this becomes integral from 0 to 1, and then I have x times 1 over 4 plus 1 over 4 square root of 1 plus 8x, and then minus 2x squared plus x. I multiply the minus sign by both of them, dx. So this is the integral that I have to calculate. Okay, so what I do now, actually, I start decomposing this one integral here. So I will actually write 0 to 1. So you see that I multiply this in, it becomes 1 over 4 times x dx. So I pull 1 over 4 out. Yes, so it becomes x dx. And then let me write with these simple ones first. So I multiply this by x, and then I multiply this also by x, and I decompose my integral. So this becomes minus 2 integral from 0 to 1. Yes, and then I have x to the power of 3 dx. And then I have plus another integral from 0 to 1 x squared dx. These are actually very simple. The only problematic one is this one. So I multiply this x inside, and then 1 over 4 is a constant, so I can pull it out. It becomes integral from 0 to 1 x square root of 1 plus 8x dx. And then I have to calculate 4 integrals, but these are simple. So let me just write the ones that are simple. So this becomes equal to 1 over 8 x squared, because this is x squared over 2, this 2 and this 1 over 4 becomes 1 over 8, then I have x squared, I have to run it from 0 to 1, then it becomes 1. So that is just simply 1 over 8. Here I will get x over 4, this 2 simplified by this 4, 2 remains in the denominator, and between 0 and 1 it becomes minus a half. And the next one is very simple, it becomes a third. Okay, and then it becomes plus 1 over 4, and for simplicity let me call this integral m for the time being, and then write 1 over 4 times m. And if I simplify the first few fractions, I take the common denominator here is 24, yes, so this is 3 times minus 12 times and then plus 8 times. So it is just minus 1 over 24. So let me clean this, minus 1 over 24. And then I have plus 1 over 4m. And I have to calculate the integral m. Okay, so I will take this integral with me to the next page. So the integral that I am supposed to calculate m is equal to the integral from 0 to 1 x square root of 1 plus 8x dx. So one way to calculate this is the method of substitution. So I introduce u to be square root of 1 plus 8x. But before differentiation, I raise both to power 2. So this becomes this expression, and I differentiate both. Then the left side becomes 2u du, and the right side becomes actually 8 dx. Now I am looking for dx, so I divide everything by 8. I get 1/4 u du. u. So that is what I have for dx. Okay, but then I also need to take care of new limits after introducing this. Okay, so I know that x goes from 0 to 1. So this would then imply that u goes from, if x is chosen to be 0, I put 0 here, square root of 1 is 1. So the lower limit for u becomes 1. If I choose x to be 1, I put it here, it becomes square root of 9, which is 3. Okay? And of course here I also need x in terms of u, but I take this and isolate x to find x in terms of u, and the result will be simply x is equal to u squared minus 1 everything divided by 8. So this means that the m integral is the integral, instead of from 0 to 1, it goes from 1 to 3. Instead of x, I write u squared minus 1 over 8 times, instead of this integral, I put u, and instead of du, dx, I put 1 over 4u du. So what happens? That 1 over 4 goes outside. That u you see here will be multiplied by that u. It becomes u squared, then I have du. And this 1 over 8 goes out, so it becomes 1 over 32, integral from 1 to 3. And then when I multiply u squared in, it becomes u to the power of 4 minus u squared, and then I have du. But then the integral is simple here, so this becomes 1 over 32. 1 over 5u5 minus 1 over 3u3. And then it goes from 1 to 3. So I put 3 there. So this becomes 1 over 32. If I put 3 there, what happens? It becomes 243, 3 to power 5 divided by 5, minus 3 to power 3, which is 27 over 3. And then I put 1, so it becomes minus 1 over 5 plus 1 over 3. I put 3 and 5 and subtracted them. So what can I write? I can simplify this a little bit. 1 over 32. Okay, I will take this one with that one. It becomes 242 over 5. And then minus 26 over 3. Okay, for simplicity, let me factor a 1 over 15 out. This becomes 1 over 32. Of course, you can calculate these things using the calculator. And then what happens? It becomes 726 minus, if I multiply that by 5, 130. Yes? So if I factor a minus 1 over 15 out, then 3 will be multiplied here, and 5 will be multiplied here. And then if I subtract them, it becomes 1 over 32 multiplied by 15, and that number is 6 and 9 and 5. So the answer is 596 over 32 times 15. Okay. And I think we can also simplify things a little bit. But let us, for the time being, keep it like this. So this is my m value. But of course, the m value should be plugged in here. So what I'm supposed to do, I have to calculate this one to calculate the second integral here. Yes? Minus 1 over 24 plus a quarter of m. So the integral I2 is equal to minus 1 over 24 plus a quarter of that number, 596, and then divided by 3, 2, and 15. Yes? But then what can I do? I can simplify this 4 by that. It becomes 150 is 600, so it becomes 149. Yes? So this becomes so I2 is equal to minus 1 over 24 plus 149 over 32 times 15. Okay, so let us keep this. Of course, I can simplify this better, but I have not calculator available. So let us hope that something happens in the future that these numbers can be simplified easier. Okay, so let me keep this one. So that is my I2. Okay, now the problem is calculating I1. Now you understand what I wanted to explain here. Because when I want to calculate I1, the lowest possible value, this is integration on I1 is this one. I want to give the name of I1 to this, and then you see the domain of integration is D1, and then I mentioned in the beginning that this is considered to be D1. I'm considering this to be D1. Okay, so if this is my domain, and still I want to give the role of the free variable to x, so this is the lowest possible value for x, which was -1/8 from the beginning of these videos. And then on the right hand side I have 0. So x goes from -1/8 to 0. But for any choice of x, if I go vertically upwards, then what's happening? I have two cut points again. Both of them are on the green curve, but be careful. These are two different branches of green curves, the green curve as I explained earlier, because this part of the green curve is below 1/4, which is represented by this equation, but with a minus sign. And then the highest value is on the other branch, which is exactly represented with the same equation, but this time with the positive value. So let me just try to write something here that you still know. You have the picture in front of you. So here x, which is chosen to be my free variable, this time goes from -1/8 to 0. But for any choice of x on this interval, the y value actually goes between these two branches of the green curve, meaning 1/4 minus 1/4 square root of 1 plus 8x and the positive branch. Yes? So that's what I want to do, the same thing here. So again, I will give the role of the free variable to x, but for x I choose these limits, but for y I use a little bit more complicated limit. I hope that you have already started appreciating the symmetry arguments for calculating this integral. Okay, so now I go to the next page. I want to so let me calculate I2. I2 is integral on domain 1 x dA, and then as before I give the role of my free variable to x. So x goes from -1/8 to 0, and then I have another integral with integrand x, variable is y, but it goes from 1/4 minus 1/4 square root of 1 plus 8x up to 1/4 plus 1/4 square root of 1 plus 8x. Okay? But again, let me do the calculations here. So x is the constant because integration is actually with respect to y, and the integral of dy is simply y. I have to calculate it from this limit that you see here up to this limit. So this means that instead of this y, I put the upper limit and then the lower limit and subtract. But if I do that, you see that when I write this minus that, what happens? This simple part unfortunately cancels out, but this harder part adds up. Yes, and it becomes 1/2 square root of 1 plus 8x. So let me just write the answer here. So then it becomes integral from -1/8 to 0, and then I have 1x out, and then I have 1/2, which I write here, and then I have 1 plus 8x dx. So that is now the integral that I have to calculate. It is not, by the way, that bad, because the integrand at least is exactly the integrand that we had on the previous page, as you see. Yes, but of course the limits are different. So if you don't mind, let me just use the same integrand with the same trick, But what are the limits? This time, the lower limit is minus 1 over 8. If I put it here, what I get for u is 0. And the highest limit is 0. When I put here, I get 1. So instead of having 1 to 3, I will have 0 to 1, but the same integrand. Yes? And let me also be careful about this coefficient. Yes, that coefficient is coming from here and this one. So this is still the same. So what I will get is, but of course I have also a 1/2 already here. So this becomes 1 over 64, integral from 0 to 1. Okay, I forgot. Let me see. U to the power of 4 minus u to the power 2 du. Yes, so that's my integral. And then if I calculate that, it becomes 1 over 64, and then I have 1 over 5u5 minus 1 over 3u3. And then I have to run it from 0 to 1, but then it becomes extremely simple. It's 1 over 64, and I get 1 over 5 minus 1 over 3. And again, if I factor the 15 out, then I will have 3, and then I have minus 5, which is minus 2. So I simplify that, it becomes minus 32 times 15. So this is my integral I2. Now, hopefully, if I haven't done something wrong, this is my I2. I go to the previous page. This is my I1. I think bringing I2, I1 on this side is easier to remember. So you remember I1 is actually minus 1 over 32 times 15. Okay, so what I do, so the whole question mark is I1 plus I2. I1 is minus 1 over 32 times 15 as I have it on the previous page. And then I2, let me write the second fraction first. Yes, and then minus 1 over 24. Okay, so what I can do, at least I see the denominators here are the same, so I subtract the numerators. It's 148 divided by 32 times 15, and then I have minus 1 over 24. And then I have to start simplifying things. So if I divide this by 2, it becomes 74. And if I divide it by 2, it becomes 37. So I can divide this by 4. So it becomes 37. And this becomes 8. Yes. And then 8 times 15 is 120. So what I get is 37 over 120, and then the other one I multiply by 5, it becomes 120 again, but minus 5. And if I subtract them, it becomes 32 over 120, and then if I divide by 8, the numerator becomes 4, the denominator becomes 15. Okay, now I am relieved. So I get the same answer as we calculated without the symmetry arguments. As the final point of this video, I think that's also good to see how you can use Wolfram Mathematica to calculate these double integrals on given domains. Yes, so I'm using Mathematica Home Edition. This is version 13.2. And I know that this feature that I'm going to discuss now is actually added to Mathematica 10 and afterwards. So the domain of integration is y greater than, so I put the greater than and then I put in equality sign immediately after that, so it will generate what I want, 2x to the power of 2 minus x, and then and in Mathematica I type 2 of these symbols consecutively, and then x is greater than or equal to again 2y to the power of 2 minus y. So you remember that was the domain. Inequalities defining my domain. To make Mathematica understand that, so I use this implicit region that you see here. So I use implicit region, but the syntax is like this. So I have to put these two equations in curly brackets and then a comma, and then I have to say Mathematica this is in 2 dimensions, so I put x and y variables in another curly brackets, and then I close the square brackets, and then I put semicolon, meaning that I define my region. And of course I give this region a name, so let me call it D as my domain. Okay, and then I press Shift Enter. So now, okay, so D is already protected for the differentiation, so let me call it region R. Okay, and then Shift Enter. So now Mathematica, this region is defined for Mathematica. And then, as usual, if I want to integrate, I just write integrate. So this is integration. Do you remember your integrand is x? But here you want to tell Mathematica that my domain is R. So what you need to write, you need to put a comma, and then you put curly bracket x and y, curly bracket closed, and then you say it belongs to the domain R. How should I use that? I press escape button, and then I just write EL for element, and then you see that this pops up out, and then I choose it. It means it belongs to R. So here my integrand is x, the domain of integration is R, and when you write x and y, it already tells Mathematica that this is a double integral. So then you Shift Enter and you immediately get the answer. So the answer we get, 4/15, is the correct answer. Okay, so I know that this is a very long video, but I hope that you learned a lot of things by looking at different parts of the video. Okay, so I hope that you enjoyed the video. Until the next video, be safe and goodbye. Thank you.